Situation, guys, we are behind, right? So normally I would teach this section like in 3 different days, and we're just gonna hit it. We're gonna do 3 days and 3 for 1 deal. All right, 3 for 1. Let's begin. This page of notes that you have here is mainly on vocabulary. And I'll be honest with you, the only thing you really need to know are a couple of these words. There's not that many vocabulary questions, or especially these types of vocabulary word questions on the final. So we're just going to skim over it. We already know that a polynomial is just many terms. And this is a new word that we're going to be using, the word degree. Degree means highest exponent in your polynomial. Okay. Degree means highest exponent in your polynomial. So if I looked at this polynomial, what would the degree be? Help me. What is it? Quick. Tell me. The degree is 3, highest exponent, right? Okay. So that is a 3. The degree is 3. Okay. So we know what degree means? Yes. Okay, great. Degree is simply the highest exponent of the variable or variable expression or polynomial. Standard form, that's just the way it looks. And we have covered standard form when it comes to parabolas, but the standard form when it comes to polynomial, I mean, it's here as well. It's simply organizing your polynomial from the highest exponent down to the smallest, down to the constant at the very end. As a matter of fact, the word constant is another vocab word that we should know. Constant is simply the number to the far right of a standard form polynomial without a variable. Okay. So this guy right here is not in standard form. It's not. Okay. So if I asked you rewrite it in standard form, what would you do? What would the first term be if I wanted to rewrite it in standard form? Negative x to the third, and then plus 5x squared, and then plus 2x, and then minus 4. Okay, now it's in standard form. Great. So normally, if this were a regular day, if we weren't behind, I'd like tell you all this vocab and then give you some problems like, hey, rewrite this in standard form. And then I would ask you, like, what is the degree? You would say the degree is 3. And then I would say, what's the constant? You would say the constant's what? -4. And then there's this other vocab word, leading coefficient. Leading coefficient. So leading, obviously, it's in the front. Coefficient, what is a coefficient? It's the value in front of your variable. So if I said, what is the coefficient of x squared? The coefficient of x squared is 5. If I said, what is the coefficient of x? That would be 2. Coefficient is simply the number in front of your variable. Now, if I say, what's the leading coefficient? That's saying when it's in order, what number's out here in the front? The leading coefficient is -1. You guys got the vocab. All right, and down here, we classify polynomials. The first name of a polynomial is based on the degree, which means highest exponent. The last name is based on how many terms you have. If it's only one term, it's a monomial, 2 terms binomial, 3 terms trinomial. And we have some examples down here. Like right here, we have 4x to the third minus 8x. The first name would be based on the degree, which is 3, and that would be cubic. And there's only 2 terms, so 2 terms of binomial. So this right here is called a cubic binomial. Okay. So like I said, if we had a lot of time, I would also throw this on quizzes and tests where I give you a polynomial and I tell you, give me the first and last name based on the degree and how many terms that you have. But it doesn't come out in the final, so the heck with it. We're just going to move on. On the back side of your notes that you just have right there, you have this worksheet. But you know what? Even before this worksheet, let's go to our notebooks. So we have covered functions and function notation in the past. I hope we remember it. If not, I'm just going to review it real quick. You see, this is function notation right here. G of x is just the name of the machine, right? G of x is the name of the machine. It could have been called f of x. It could have been called q of x, r of x, right? Most of the time we use f of x. Right here, they're calling it g of x, okay? Now, the notation says right here, how do you evaluate a function? If I say find g of 2, this is function notation, and that's a quick way of saying, I want you to go to the g of x function, and I want you to plug in 2 into the x value and simplify. You see, that was a lot of words coming out of my mouth. I could just say find g of 2, and that says it all. This notation tells you to plug in 2 into x and do the math. So right now in your notebooks, go ahead and copy down g of x equals x squared plus 1, and then write down find g of 2. You don't have to write down everything else. Just write down the g of x function, which is x squared plus 1, and then write down find g of 2. So how do we find g of 2? Well, you're going to rewrite it. And what do we rewrite? It says x squared, but instead of x squared, I'm going to put parentheses squared. And then it has a plus 1. I'm going to put a plus 1. So this notation is telling you plug in the 2. So you simply plug in the 2 right there, and you do the math. You could do it in your head. You could do it on the calculator, whatever you want. The answer is what? 5. Okay, so g of 2 equals 5. Great. Now, we've already done that in the past. But on today's section, it gets a little more entertaining because I'm going to ask you to do g of 2x. This does not mean g times 2x. It means g of 2x. So I'm telling you to plug in the variable expression 2x into that variable x. So again, just like before, you're going to rewrite this thing. G of x equals x squared plus 1. But what are we plugging in? This time we're not plugging in a number. This time we're plugging in that blue 2x. So I'm actually going to plug in that blue 2x. And hopefully you're keeping up here. And then we're going to do the math. How do I do the math? It says 2x squared. That's just saying 2x times 2x. What is 2x times 2x? 4x squared. And then you bring down the plus 1. And you can't do that. So that's it. That's your answer. So g of 2x is equal to that 4x squared plus 1. Pretty easy, right? Could it get more fun? Heck yeah. Let's try g of x plus 3. Okay, so we're actually going to take the binomial x plus 3 and we're going to plug it in to that x spot. Okay, so once again, we're going to rewrite it. Instead of x squared, I'm going to put parentheses squared and then plus 1. And what am I plugging in right here? I'm going to plug in that binomial x plus 3. So let's do that. Plug in that binomial x plus 3. And you know what? Just to keep it looking nice, I'm going to highlight it. And now we got to do the math. Okay, so let's do the math. That's going to be simply x plus 3 times itself 2 times. X plus 3 times x plus 3. And of course, you still have the plus 1 over here. But you got to do multiplication before adding. So we're going to distribute, combine like terms, and then at the very end, deal with that plus 1. So x times x, x squared. X times 3, positive 3x. Positive 3 times x is another positive 3x. Positive 3 times positive 3 is positive 9. And then you bring down that plus 1, and now you could combine all the terms that are alike. Those middle terms, 3x and 3x is a total of 6x's. Then 9 plus 1 is 10, and the x squared comes down. So what is the answer to g of x plus 3? G of x plus 3, the answer is this quadratic trinomial right there. What do you think? Fun? Yay, are you guys awake? Yes, okay. So if we go to the worksheet, we have some fun stuff, like right here in the middle portion of the worksheet. It says P of X is this, R of X is this. Again, P of X is just the name of this machine. R of X is just the name of this machine. So I could tell you find P of 8A. So you're going to actually plug in 8A right there, square it, then multiply it, and then put the minus 4 at the end. Or I could say go to the R function and plug in the A squared right in there and the A squared right in there and do the math, right? But you get the idea, right? Now, there's only going to be like one of these questions on the final exam, and I hope we understand it. Now, the first part, it doesn't even have variable expressions to plug in. The first part is just plug in numbers. I mean, that's algebra 1 stuff, technically. P of -2, I want you to go to the P function right here, number 8. Go to the P function, plug in -2. So how would you do that? You would say 3 parenthesis to the third minus parenthesis squared plus 2 parenthesis minus 5. And you're going to plug in this case, -2. So we're going to do P of -2. So you're going to plug in the -2 right in there. And you can do all that math, and hopefully you don't make a mistake. And you can even do it on the calculator. But even if you do it on the calculator, you're typing in a lot of buttons. It's easy to make a mistake on a calculator. So what I want to do right now at this moment is share with you how we could use what we most recently learned, synthetic division, but as synthetic substitution. Okay. So in synthetic division, we have this like backwards capital L, and we normally plug in a number right here. And you could use this process, this synthetic process, to substitute the -2. Now, if you plug in a -2 right in there, and then you make a list of numbers of your coefficients, representing every coefficient from your largest power 3 down to the constant at the very end, -5. Again, if you have any missing powers, you have to fill them in with 0. Power 3, yeah, you got a coefficient. Power of 2, got a coefficient. Power of 1, got a coefficient. Constant. So there are no missing powers. So my list of coefficients will be the 3 that's on the x to the third, the -1 that's on the x squared, the +2 that's on the x, and the -5 that's all by itself the constant. Okay, so check this out. As you go down, you combine. So 3 plus what? 3 plus 0 gives you 3. As you go up, you multiply. -2 times 3 is -6. As you go down, you combine -1 and -6. That gives you a -7. As you go up, multiply. -2 times -7 is +14. As you go down, combine. 2 plus 14 is 16. As you go up, multiply. -2 times 16 is -32. Normally, this is the remainder over here, -37. However, this wasn't a division problem. This was, we're using synthetic substitution. So we plugged in a -2 and we got out a -37. So in other words, if I were to do all this math right here, the -2 to the third times it by 3, the -2 squared, put a negative in front of that, and do all this math, your answer will be -37. Just wanted to relate it to the last synthetic division, but instead of division, it's synthetic substitution. So you could use synthetic to substitute a value and get out an output. And this is actually pretty cool because right here, this is the input, this is the output, and that's technically a coordinate, a point of the graph if you were to graph it. Okay. Um, so if you were to go to Desmos and type this in, this would pass through the point -2, -37. Okay. Anyway, normally I'd say that's it. That's a lesson. I want you guys to practice and I want you to practice, but we're going to move on. Down here, we have graphs. We got to learn how to analyze these graphs. Okay. In order to understand graphs, I want you to go to Desmos right now on your Chromebook. Go to desmos.com, go to the graphing calculator app on Desmos, and I want you to type in a bunch of odd degree functions. Y equals x, y equals x to the third, y equals x to the fifth, y equals x to the seventh. Type them in, and let's just look and see if we could conclude anything. Hold off on that. Go for it. Type it in. I'm going to pause it. I'll unpause it once everybody has it typed in. Okay, so what do we notice about these graphs? Here, oh wait, here it is. They go loopy loop. I just typed them in right here. So all these odd degree functions, odd degree, they end up down here on the bottom left and up here on the top right, all of them. Is that a coincidence? No, that's something that we need to observe, recognize, and learn, right? Any odd degree function is going to end up here and down here. Now, these are the most basic types, right? Like we have y equals x to the seventh. Now, if you were to put like plus x to the fifth minus 3x to the second plus 4x, take away 7, you put a bunch of other stuff right here, the end behavior will be the same. It'll end up it'll end up down here and up here eventually, but something else may happen in the middle. Like maybe it goes like up and then down and then up and then down like that, something crazy, but it does still end up over there and down here. Okay, so the first thing I want you to understand about these odd degree functions is the end behavior, and I want to introduce the notation. Okay, so maybe in your notebook, I know you can't get this picture in your notebook, but in your notebook, maybe you could do a XY plane like this, and you could draw, or you could draw one of these that squiggles right through it like that. And we could say the end behavior of any odd degree function is, and I'm about to write it down. You've never seen this before. We're going to use this end behavior notation. All right. And I want you to really pay attention, think about it. It'll make sense if you're paying attention. If you're falling asleep and you look at it 5 minutes from now, you'll be like, what the heck's going on? But if you pay attention, you'll be like, oh, I get it. It's easy. Let's begin with this. As x approaches negative infinity, okay, go ahead and write that down. As x approaches, it's an arrow. It's not an inequality, it's an arrow. As x approaches negative infinity, your f of x's, your y's approach negative infinity. What the heck is he talking about? Okay, pay attention. Check it out. Check it out. When I say as x approaches negative infinity, here's your x number line. Which way is negative infinity on the x? To the left or to the right? To the left. So this is really saying as you look to the left, what's happening with your graph, with your y values? Are your y values up here or down here? As you go to the left, what's happening to your y values? They're going down. So as you go to the left, as you go to negative infinity on the x, your y values are also going to negative infinity on the y. Okay, it might be confusing. It's the first time you hear it. Now let's look at it to the right. As x approaches positive infinity, that means as you're looking at it to the right on the x, then your y values, your f of x values approach what? Positive infinity. As you go to the right, where are your y values at? They're up there in positive infinity. Cool. I hope you wrote that down because we got to practice writing down this end behavior. And I'll tell you this right now, there's one question on the final exam that has this end behavior stuff. Okay. Not only that, we're going to have it on the test next week. Not this week, next week. So we need to get comfortable with this notation. And in reality, it could be written backwards. I could tell you as you look at the y going down, then your x's are going to the left. You could say it backwards as well. Okay. Anyway, let me ask you this. What if I were to go to all these on Desmos, and what if I change the a value to a -1 instead of a +1? So right now, go ahead and go to Desmos, since you have it there, and go ahead and put a negative sign right there, right there, right there, and right there. What do you think is going to happen? It's going to, okay, with parabolas, you had a parabola that opened up, and if you change that a value to a negative, what would happen? It would reflect over the x-axis. But in this case, since it's not a parabola, but you have an end behavior down here and end behavior up there, if you put a negative in front of there, what's going to happen? It's going to reflect over the x-axis. So it's going to reflect like the whole thing is going to flip. Go ahead and do it so you could see it. And this is what you should see. Everything flip. Yay? Okay. So just to practice writing end behavior, let's write down the end behavior on this one. Okay, maybe in your notebook, you could just do a XY coordinate plane sketch and then just do one of them that goes like this, right? And you could say, you could put like right here, the a value is -1, right? The a value is -1. So what can we say about the end behavior here? As x approaches, you know what? I'll let you guys pick. You don't have to say negative infinity. You can say positive infinity. Which one do you want to do? Negative or positive? Positive. Okay, so let's try positive this time. As x approaches positive infinity, your f of x approaches what? Think about it. If you're saying x approaches positive infinity, you're looking at to the right this time. Now, where's your graph at? Is it above on the y's or less on the y's? Down here to negative infinity. So as x approaches positive infinity, your y's approach negative infinity. Yay? I probably would have started with as x approaches negative infinity, your f of x approach what? As you go to the left, your y values are where? Positive infinity. So it doesn't matter which way you're looking at it, right? And you could even write your y value first. You could say, as your y values are going to positive infinity, where are your x values going? As your y values are going to positive infinity, your x values are going to the left. You could say it backwards as well, okay? Do we understand what I'm explaining right now? If not, please let me know. Again, this is end behavior, describing how it behaves at the end. Like I said, if you add on other things right here to the -7, I mean to x to the negative to the no, I'm sorry, I can't even speak right now. If you add other things to that degree 7 to the negative x to the 7th, and if you put like plus 6x to the 3rd, plus 5x minus 7, other things may happen, but it will end up here and down here. That's how it's going to end up. Other things may happen right here in the middle, but it's going to end up there and down here. Yay? Now, what do you think is going to happen if instead of odd degree functions, we typed in some even degree functions, okay? And go ahead and do that. Type in y equals x squared, y equals x to the 4th, y equals x to the 6th. And we should all be comfortable with even degree functions because we've spent so much time with parabolas, right? So what does y equals x squared look like? That's a parent graph of all parabolas that has a vertex at 0, 0, has a pattern 1, 1, 2, 4, 3, 9 from the vertex. And here it is. If you type in all those even degree functions, they all kind of look like parabolas, right? They all have an end behavior up here and up there. Now, of course, if you added on other things like y equals x to the 10th, if you added on like plus x to the 7th minus x to the 6th, plus 4x to the 3rd, then other things will happen here, but the end behavior will still be up here and up here. Does that make sense? Okay. What if I were to put a negative sign as the a value on all of these? What would happen to all these graphs? So again, if I were to put a negative in front as an a value, a -1, what would happen to all these graphs? They get reflected over the x-axis like that, right? Well, not exactly like that, like this. Cool. Let's practice writing end behavior on this guy. Maybe in your notebook. As a matter of fact, you know what? This page I gave you, it has an area for this stuff. Up here on the top right, I gave you this page of notes. On the top right, it says if your polynomial function has an even degree, then the end behavior will be in the same direction. So we know that y equals x squared, y equals x to the 4th, any even degree, it's going to end up with the end behavior up here and up there, right? The parent graph is the U-shaped curve. X to the 4th also ends up here and up there. X to the 6th also ends up here and up there. Of course, if you added on other things, then other things will happen, like in this area, like maybe it'll go down, up like that, but it'll end up always end behavior up here and up there. Okay. So let's write that down. Let's describe the end behavior as x approaches negative infinity, f of x approaches what? Okay, think about what does this mean? What direction is this going? Here's your x-axis, negative infinity. Where's negative infinity? To the left. So where's your graph at in terms of the y values? Are they positive infinity or negative infinity? Positive infinity. So as x approaches negative infinity, f of x approaches positive infinity. So right here, as I look to the left, it goes up. And now let's write down as I look to the right. As x approaches positive infinity, then my f of x values, my y values go where? Also positive infinity. Okay. So one thing we could conclude here is if you have an even degree function, the NB and the a value is positive. The a value is +1, a value is +1. As long as your a value is positive, it's going to have an end behavior up here. That just means how it behaves at the end. Going this way, it goes up this way. Going to the right, it goes up this way. Okay. Now, what if you had a negative a value of 1? Then, and this is an even degree function, then your end behavior will be down here and down there because the a value of -1 causes a reflection over the x-axis. So the end behavior will be down here and down there. Does that make sense? Okay. So let's write down the end behavior notation here. As x approaches -infinity, f of x, whoops, f of x approaches what? -infinity. And as x approaches positive infinity, f of x approaches what? -infinity as well. Right? As you go to the -infinity on the x, you're going down on the y. It's going to -infinity on the y. As you go to positive infinity on the x, you're going down to -infinity on the y. Does that make sense? So this is for even degree functions that have a negative a value. Even degree functions have a negative a value. Um, if your polynomial function has an odd degree, then the end behavior will be in opposite directions. Okay. So how about this? Just to really understand odd degree functions, let's actually by hand graph y equals x to the third. Okay. So here's my xy plane, and I want to graph it old school input output table. I want to plug in some easy numbers like -2, -1, 0, 1, and 2. Let's start with 0, the easiest one. What is 0 to the third power? Okay. What is 1 to the third power? 1 times 1 times 1? 1. Okay. So if I went 0, 0, 1, 1, it looks like it's a straight line. But when I go 2 to the third power, what's 2 to the third power? 8. So if you think 2, 8, man, that's way up here. It kind of looks like half a parabola, half of a really narrow parabola. But then if you go to the negatives, -1 on the x, -1 times -1 times -1, that's -1. If you go -2 times -2 times -2, that's -8. So -1, -1, -1's right there, and -2, -8 is down here. So that ends up producing like a little snake-like curve, like that, right? So the end behavior is down there and up there. And that's when your a value is positive. If your a value were negative, it would reflect over the x-axis and have end behavior up here and down there. Does that make sense? Okay. So let's write down this end behavior. As x approaches -infinity, as you look to the left, where are the y values at? Going to positive infinity or negative infinity? As you go to the left, is your blue graph going to positive infinity or negative infinity? Negative infinity, right? So as you go to the left, it's going down. So as x approaches negative infinity, your f of x approaches negative infinity. As x approaches positive infinity, your f of x, remember, your x approaches positive infinity, your f of x approaches what? Positive infinity. Do you get it? Yay? Okay. Now, those are all with the a value of 1. If you change them to -1, then it would just reflect over the x-axis like that. Okay. So it would be like this. Instead of down here and up there, it's going to be up here and down there. So the end behavior as x approaches negative infinity, f of x approaches positive infinity. As x approaches positive infinity, f of x approaches negative infinity. Anyway, normally that would be a second day. Let's jump to day 3. We're going to analyze these stinking graphs and we're going to say a lot of information about them. Okay. And we're also going to learn a little bit of vocab words. You don't have this on your paper, so just pay attention to the screen right here. Um, when I take a look at this guy right here, Is this an odd degree function or an even degree function based on what we've talked about so far? It has to be even, right? It has to be even. Think about this. There's an even amount of arrows going down. If it were one down here and one up here as an end behavior, then that would be an odd degree function. Make sense? Okay, so it's an even degree function. So could it be y? Oh yeah, and what about the a value? Is the a value positive or is it negative? Does it open up or down? Opens down, so it's the a value is negative. So we know that this polynomial function, it could be something like y equals x to the, and it has to be a negative because it's the a value is negative. So there's a negative, and the degree, it has to be even. But we're gonna even go a step further. It can't be the power of two, right? It could be a higher even degree. Why can't it be the power of two? Well, first of all, the direction change tells you the minimum degree it could be. So check this out. From left to right, it's going up, that's one. And then all of a sudden it's going down, that's two. Then all of a sudden it's going up, that's three. Going down, that's four. This degree has to be at least the power of four. It could be six, could be eight, but it has to be at least four. And since we're on this picture, this is a great picture, this great graph. We might as well talk about a couple of vocab words. We remember maximum and minimum values, right? Okay, so we're gonna add on a little bit to that. What is the max value of this graph right here? Or how about this? Let me ask it a little in a more fancy way. What input, what input would give you the maximum value? Would the input of one give you the maximum value? Input of two, input of three, input of negative something? Tell me. The input of negative two will give you the maximum value. So if you want, you could sketch this little graph in your notebook. It doesn't have to be perfect, but just, you could do a XY plane like that, and then just draw something kind of like that. And then up here, you could put a dot. And even though we know this is as the maximum value, we're going to label it absolute max value. Absolute max value. Okay. Why? Because that's absolutely the highest point in the entire graph. Now, if I were to zoom into this guy right here, that also looks like a little parabola, and it technically also has a max value right there. Yes or no? Yeah. But right here, this is not an absolute max value. This is what we call a relative max value. Relative. Now, relative to what? To this area. It's kind of like this. If I said, everybody stand up, let's find out who's the tallest person, right? There's going to be the tallest person in this class, but that's relative only to this class, not to the whole world, right? So right here, this is a max value, but it's only relative to this area, because if I look at the whole graph, there's this one that's even bigger, is an absolute max compared to a relative max. Do we understand the difference? That will be on the final exam as well. There's one question with regards to relative max, absolute max, relative min, absolute min. Okay. So again, this guy up here, absolute max. This guy down here is relative max. Okay. Now, is there an absolute minimum value in this guy? Is there an absolute minimum? No, there's not, because it actually goes down forever. But there is a relative minimum. What input would give me the relative minimum? Positive one. The input of positive one, the x value of positive one, will take me to that relative minimum. So if you drew this, not perfectly accurate, but if you drew it in any way that's similar to this guy right here, you could label it relative min. There is no absolute min because the absolute min goes down forever. What do you guys think? So, man, it's a long lesson, but we really have cranked out at least 3 questions on the final. Okay. Um, so right here, let's go to a different one. Look at that guy. Oh yeah, fun stuff. Fun stuff. How about this? Yeah. What is it, an odd degree function or even degree function? Even degree function. Okay, let me just write that down. Even degree. Okay, how about this? Is the a value positive or negative? The a is positive. Why? Because it's opening up, kind of like a parabola. A parabola, if the a is positive, it opens up. If it's negative, it opens down. So we know that the a value is positive because both end behaviors are up here and up here. There's two arrows going up. That's an even degree. Okay. Um, but if I said what is a good degree for this one that you see here? Like, what is the actual degree? Is it the power of 2, the power of 4? Those are even degrees. Is it the power of 6, power of 8? What do you guys think? Based on the number of directions that it has, going down, that's 1, going up, 2, 3, 4, 5, 6. So yes, this could look like this: y equals x to the power 6 with some other stuff, right? So yes, the degree for this one would be 6, at least. I mean, it could be 8, it could be 10, but it can't be 4 or 2. It has to be at least 6 or greater based on the directions that it has. How about if we wrote down the end behavior as, and you know what? Let me get tricky on you. I'm going to throw it backwards at you. As f of x approaches positive infinity, as your y values are going up, does it matter if you're going to the left or to the right for it to go up? No, it doesn't. So you could say as f of x approaches positive infinity, uh, your x's could go to the negative infinity. Or you could say as f of x approaches positive infinity, you could also say your x's go to positive infinity as well. I wouldn't have written it this way. How would I write it? I would say, okay, as x, I always like to look at the x first, and I want to look at it to the left. As x approaches negative infinity, f of x approaches what? Positive infinity. And as x approaches positive infinity, that's saying as you look at it this way, which way is the y values going? Positive infinity. Great. It looks like you guys got it. And we're going to continue this tomorrow. All right, guys? Thank you for your long attention.